Yeah, so just a quick update that we are waiting for everyone else to join. Hopefully in a few minutes, in a couple of minutes, we'll start.
Okay. Thank you.
Okay, I suppose we can get started slowly, and then hopefully everyone else will join pretty soon as well. Do you know if Bahman is going to join, or should we wait for him?
So I checked with him. He's not online. Let me check with him. Till then, we can get started, I guess. Slowly.
Yep. Yeah, sure. Can you make me the host, by the way?
Yeah, sure.
Thank you.
Just give me 1 second.
Okay, thank you.
No worries.
Yeah, thanks. All right, so I'll share my screen and
Ci ha chiamato
if...
ho imparato.
Cosa?
Ho chiamato subito come fa David.
Sì, sì.
Ho imparato da lui. No, ma giusto 5 minuti.
Don't know, but we are getting someone...
Scusami, aspetta, io volevo...
Okay, thanks. All right, so I hope everyone can see the presentation.
Yes, it is visual.
Yes.
Okay, great. So yeah, thanks for joining this talk on the role of forecasting electricity demand and societal decarbonization. My name is Hussein Kazmi. I'm an FW research fellow at the University of Leuven, where my research is basically around machine learning, optimal decision making, and smart grids. So this talk is pretty much in line with the stuff that we work at here in Alecta as well. But all in all, this is going to be a pretty high level introduction. So it's not really going to be covering a lot of research topics or anything like that. So if you're already an experienced practitioner, then this may be a bit basic, but hopefully you'll still get something out of it. All right, so also the video is being recorded. So if you're not comfortable with that, then please let us know at this point. But otherwise the meeting will be recorded. Okay, so then to get started, this talk is going to be divided into two parts. The first one is going to be an overview of the theory. Why do we make electricity forecasts? Who makes these electricity forecasts, and what exactly do they forecast? So that is going to be covered in the first part, which is going to be in the form of a PowerPoint presentation. That's probably going to take like 30-40 minutes or something like that. And then in the second part, we are going to take a look at some actual Python code that I will share with everyone. And then we will have more like a walkthrough from a Jupyter notebook on how do you actually get to make these forecasts. And what we are going to start with is forecasting electricity demand in the entire country of Belgium. And then we will show you how you can go from very bad forecasts to things that perform reasonably well in like less than half an hour. And then we will conclude with some tips and tricks on how to further improve those forecasts. Okay. So the first order of business is, why do we actually need to make these forecasts, and why is this an important and interesting problem, and how does this relate to societal decarbonization? So overall, the idea is that in the electrical network, electricity demand and supply need to be balanced at all times. And this is frequently the responsibility of the transmission system operator to make sure that whatever is happening on the demand side. So for example, if there is a lot of electricity demand because it's cold, then there has to be sufficient supply on the supply side or generation side to make sure that this demand can be met in a reasonable way. When the supply is not equal to demand, then we have deviations of the frequency of the grid from its nominal value, which is around 50 hertz in the case of Europe. And if this frequency deviates too much from this nominal value, then you can have blackouts and cascading failures in the electrical network. So that's more or less the motivation for why the system operator needs to have a better understanding and a forecast of where things are going to be in the next 1 day, 1 hour, 1 year, 1 decade from now. And then using these forecasts, the grid operator can actually do 2 things. On the one hand, they need to do operational optimization. So they need to make sure that they have sufficient electricity supply available. This is the operational part. But at the same time, they also need to make sure that there is some kind of design optimization going on, so that on a multi-year level, there is going to be sufficient resources to provide the user electricity demand. At this point, you may say that this is all great, but the electricity network has been operating for more than 100 years, and why is this still a relevant problem? That's a fair point. However, there are many changes going on in the electrical networks as we speak, which have made this, again, a very interesting and challenging problem. The first and foremost of these is the rapid rise of renewable energy sources in the energy mix in many countries across the world. So this primarily refers to solar generation and wind power. And if you contrast this to what was happening in the grid 10 to 20 years ago, then you would see that there was a much higher share of predictable fossil fuels on the grid, which simply meant that you wouldn't really have to rely on the sun continuing to shine for there to be electricity on the system, but you just had to have enough gas or coal or oil or whatever to make sure that there was going to be sufficient supply for the user demand. So that's the problem on the generation side, that the electricity mix is switching from a predictable fossil fuel based system to something which is more dependent on the climate than on the actual inputs that are going into the power plants. The second thing that's happening is on the demand side, which is seeing a rapid electrification of energy demand in many countries across the world. So the primary driver for this at this point in many European countries, especially, is the rise of electric vehicles. So if you see the numbers, then you already see that, for example, in Norway, there are more electric vehicles being sold at this point than fossil fuel cars. So that's already great for the environment, but that also means that there is like all this additional demand now on the electrical network that used to be met by like simple diesel or gas on the power plants. There are also other problems which relate to the rapid electrification of heating. So this was previously done using gas, but now this all has to be, well, there are many plans to replace gas completely over the next 2 to 3 decades by electricity. And what this means in practice is that the electricity demand is also continuously changing. So whatever used to happen 5 to 10 to 15 years ago is no longer representative of the grid. And whatever is happening today is also not really representative of what is going to happen 1 year, 1 decade from now. So the grid operator really needs to understand these trends and patterns in the data to make better forecasts, to make sure that there is always going to be sufficient supply to meet the actual electricity demand. So that's a key, well, that's one answer to who needs to make these electricity forecasts. There are also many other stakeholders in the system that need to do this. So for instance, there are electric utilities, there are distribution system operators, there are aggregators, there are a lot of different market players, but I don't think we have enough time to go into that. But if anyone is interested, please feel free to interrupt and ask a question at any point. However, coming back to the TSO story, the transmission system operator, this is typically done at the very right hand of this figure. So this is at least an entire region's level. So this is very high level electricity demand. As such, it is typically quite predictable. But there are still like a lot of interesting trends and seasonalities that are going through in this data set. So that's also the data that we are going to take a look at in our practical session later today. But just so you're aware that there are also many other aggregation levels at which these predictions may need to be made. The most popular one at the moment is the neighborhood level, where you may actually want to there are no problems on the distribution grid. So this is typically done behind a feeder level or something like that. Then you can also think that you can try to do this on an individual building level, because you may try to optimize the energy demand of a large commercial consumer or even residential consumers. To do so, you would need a forecast of the actual electricity demand on that building. And this can often be quite noisy because, unfortunately, if you think about it, we don't really know what we are going to do even ourselves in the next 24 hours in terms of electricity demand. So it's very difficult to make these forecasts. All in all, you have to understand that as we go from left to right, we go from human-dominated forecasts to more like climate and calendar-dominated forecasts. So on a country level, the forecasts are primarily a function of the features of data, like what day is it? Is it Christmas? If it's Christmas, then you'll probably have much less electricity demand than if it's not Christmas, or whether it's a very cold day or a very warm day or something in between. While at an individual building or device level, this is as much influenced by climate and calendar features as it is by individual human behavior. So there is a lot of stochasticity in there, and that simply means that forecasting at an individual device or building level is quite difficult. So if you're trying to do that, then be aware that this might be a challenge. The second thing is, in addition to the spatial aggregation or resolution of the data, you also have to consider the temporal aspects of the data. So what exactly is the time scale at which are you considering a forecast for just an hour into the future, or are you also considering like a forecast for the entire year? That would be easier possibly. Or if you're considering a forecast for each second of the day. Just like in the previous case of aggregation, as you aggregate more and more data together, the easier it becomes to make a forecast. So making a forecast for every single second of the day is much more difficult than making a forecast for the entire year. This should be quite intuitive, but let's take a look at this in action. So this is a picture from Elia. Elia is the grid operator in Belgium. And their responsibility, one of their responsibilities is to actually make sure that there is sufficient generation to meet the energy demand on the grid at all times. This means that they also create these electricity forecasts on the demand side to make sure that then they have or that they can contract sufficient generation capacity. What you see here is not one, but three different forecasts. So the orange curve is the actual measurement on the 5th to 12th of July of last year. So this is a typical load profile for the last year, that you have like quite a seasonal component to it. And then on the weekends, it goes a bit lower. So we will see this in much greater detail in the lab session. But for now, you should be interested in the fact that there are 3 different forecasts here. So there is the most recent forecast, which is typically made like 1 to 2 or, well, can be up to 4 to 6 hours as well. So this is like the most recent forecast that was available at that point in time. Then you have the day ahead forecast, which is typically done like 24 to 40 hours into the future. And then you have a week ahead forecast, which is simply like what you thought is going to happen today, but the previous week. And as you can see that the forecast accuracy should improve as you go from the week ahead forecast to the most recent forecast. And that's typically what we see here, that you have like this orange and green curves, which are always closer together than, for instance, this gray curve. And that's quite logical, because if you're making a forecast 1 week into the future, then you don't really necessarily know everything that's going to happen at that point in time. So that's one concrete example of how grid loads are forecast. However, you can also see on this figure that there are these other things, which are P10s and P90s. And what these refer to are the confidence intervals on your prediction. So when you're making these load forecasts, typically what you want to do is you want to know the median or the mean expectation on what you can expect to see on the grid, but you also want to see some worst case scenarios. So for example, what happens if my forecast is incorrect and my actual electricity demand is higher by 10%? Will I still be able to meet the demand on the users, or will I have to resort to some kind of stuff like grid outages or blackouts or something like that? So that's what we see in this figure. And there are a few different things that are going on here that should be of interest. So first, you can see that the orange curve, which is the measurement, is quite close to the actual day ahead forecast. That's great. But the other thing that's good in this curve is also that the confidence intervals, so the P10 to P90, you can think about this as like the 80% probability, as the fact that 80% of your predictions are likely going to be within this confidence bounds. It's still possible that you will be incorrect 20% of the time, and then the electricity demand is going to exceed or go below these bounds. But that's typically the trade-off that you have to make between narrow confidence bounds versus confidence bounds that are just very wide, but then not informative at all. So that's also another thing that you can take a look at here, that the confidence bounds shrink or expand in time, depending on the actual uncertainty that the grid operator has in their forecasts. This can take on some extreme cases, like for example, if you think about a football match and the penalty shootout happening or not happening, then sometimes this can take on a lot of uncertainty versus not that much uncertainty at all. Okay, so that is an example of an operational forecast where the grid operator is going to make use of these forecasts to make sure that there are sufficient reserves available to meet this demand. The other side of the picture is, of course, the design side, or the investment side, where the grid operator takes a look at a multi-year horizon and then decides what investments are necessary to make sure that the grid continues to operation in a sustainable and stable manner. So this is what we see for Belgium over the last, well, 5 to 7 years, that the grid electricity demand typically goes between 80 and 90 terawatt hours, well, mostly between 85 and 90. In the year of COVID, we saw this fall quite a bit. And since then, it has rebounded back quite nicely. But in the next decade or so, the grid operator expects this number to go up by 10%. But there is, again, some uncertainty in this forecast as well, because now this is not really that much dependent on climate variables as it is on the actual policies. So for instance, if there is a large uptake of electric transportation and electric heating, then that's the scenario of high load. The low load scenario would be where, for instance, like recently we heard that the nuclear plants in Belgium are going to be, well, extended in lifetime. So that means that we are going to stick with electricity for a lot of the demand. So it's this kind of policy decisions that can somehow also alter the actual load forecasts that you make for many years into the future, but that's not really something that we're going to talk about further in this talk. All right, so at this point, I suppose that's a good point to ask if there are any questions so far. If not, then we can get started with how to decide if you have a good forecast or not. So we have a question. What's the difference between P10 and P90? So yeah, that's just that the P10 is basically the lower bound and P90 is the upper bound. So basically that's just like the confidence bounds that you can have between which your electricity demand is most likely going to be. So P10 is going to be lower than P90 in this case then. Okay. So if any other questions, feel free to write them in the chat or just mention them, unmute yourself and ask. But if not, then let's move on to how do we decide if a forecaster is good or not. So this is quite a detailed topic, and unfortunately we won't have time to go through all the nitty-gritties of it, but some high-level error metrics that are in common use include the mean absolute error, the mean absolute percentage error, the relative mean absolute error, and then some other measures like the R-squared score and stuff like that. However, intuitively, it's quite obvious that, for instance, if you have this point, these green points, which are the actual observations, and then we have this one. So if this is our forecast, for instance, then you can obviously see that this is not a very good forecast because it's always higher than what is going to happen. On the other hand, if you have a forecaster that's very close to what's going to happen, then we can intuitively say that that's very good. Now, this notion can be formalized using one or more of these ideas, but mean absolute error is simply the average distance that your forecast is from the actual observations. As such, it is a good measure in the sense that it follows the same units, but it doesn't really tell us anything about how good or bad the forecast is. So one way that people do that is through the use of MAPE, or mean absolute percentage error, where you simply divide your error by the actual signal itself, and then you get an estimate in percentage terms of how much you're incorrect. Now, this works fine in many cases, but there are quite a few problems with this. Most notably, when your signal goes to zero, then this error does not really make any sense anymore. It also doesn't really tell you whether it's your forecast which is bad or whether it's just a very noisy time series that could not be forecast at all. So to rectify these problems, one solution is to use a scaled metric. So something like a mean absolute scaled error, in which what you do is you scale your error, the error of your forecaster, against the error of a very simple baseline model, which can typically be a persistence model or something like that. That's something that we will show you in the tutorial later, but this is something that is then stable enough to use across multiple time series that you can then decide where do I need to focus on improving my forecasts. Okay, so the second thing that you need to consider in terms of making a good forecast is the distribution of errors. Theoretically, what you want to do is you want to have normally distributed residuals so that there is really no signal left there anymore. It should be mean zero and with a small variance, hopefully, and that should be a good forecaster. But then we also want to make sure that there is no autocorrelation in the residuals of the forecast that you're coming up with. And one easy way to do that is to calculate the autocorrelation function on the residuals of your forecaster. Theoretically, they should look like this, that you should have at lag 0, a significant value, and then everywhere else, it should be very close to 0. If this does not happen, then that means that your forecast error still has some signal in it that you can exploit to make a better forecaster. So this is a very practical tip on how to improve your forecasters, that once you have created a forecaster, calculate the autocorrelation function of the residuals. And if you see some structure in there, that means that you can probably improve your forecaster. All right. Then you also want to make sure that your forecaster is generalizing and not simply memorizing. So this is an important concept in machine learning in general, but also holds for forecasting theory. So for instance, an example of a forecaster which would be memorizing rather than generalizing is what happened with the COVID pandemic, that we went into lockdown, the electricity demand really went quite low in many countries. And then if you have a forecaster which is not really adaptive, so it cannot adapt to recent changes, then it's simply going to continue to predict whatever was happening before the lockdowns from the pandemic. In this case, this would not really be a very good forecaster because it has, well, it's not adaptive, and it also is not necessarily generalizing to new unseen conditions. Then you also want your forecaster to be as scalable and computationally non-intensive as possible, because especially if you're working with aggregators of electricity demand, where you have to maybe make forecasts for hundreds of thousands of assets, then you don't really want to have very detailed models for each individual time series that you're modeling. So what you want to consider here is that you want a forecast model which scales well with input training examples. So as your input training data set grows, your forecaster should not really start to get too slow. You should also have a forecast model which does not really get too laggy as you introduce new training features to it. The forecast model should remain computationally tractable for all prediction horizons that you're interested in. And as you have more and more time series that you want to predict, this should remain scalable as well. So this last case is maybe not really that much of a problem in a historical sense, when we used to build ARIMA models to forecast any single time series. And then we would build a new ARIMA model for a new time series, and then we would repeat this over and over again. But really, if you have hundreds of thousands of assets, then building individual models for them is not only computationally intractable, but it's also a nightmare in terms of retaining and retraining all of these models through time. Then finally, a good forecaster also provides some uncertainty estimates. And this is quite crucial because what you want to do is you want to make a forecast which is aware of its own limitations, rather than making a very confident prediction about the future. Unfortunately, in the tutorial today, we don't really have time to cover this topic of uncertainty estimates and probabilistic forecasts. But that's really something that if you're serious about this field, then at some point you really need to move from point forecasts to interval forecasts. Okay, there are also a bunch of other things that need to be taken into consideration when deciding on what makes a good forecast versus not, but that's all we have time for this topic in this talk. Let's move on to how do you create a baseline, which is something that we discussed with the scaled error measures earlier. But again, this is a good time to ask a question if there's any. If not, then we can go on to establishing a baseline. So like I mentioned earlier, what you want to do with your forecast models is to always baseline them or benchmark them using simpler models, because so many tutorials on Medium and the internet are focused on creating deep learning based forecasting models for anything, that it's always a bit difficult to understand why exactly are we doing this. And the reason for why exactly are we doing this is quite clear, that your more sophisticated models need to, at the bare minimum, beat very simple baseline models that you can create with 1 line of code or 3 lines of code or something like that. And the most obvious example of these baseline models are, of course, persistence models. These are theoretically used quite widely in the electricity forecasting literature to baseline and benchmark your models. What this does is that it simply copies the past as your forecast for the future. So for instance, if you think about the electricity demand on Thursday in a country, then that would be theoretically quite similar to the electricity demand on Wednesday. And that's a reasonable first estimate. Now, you can also always go for some other kind of seasonality. So you could say that my forecast for Thursday is going to be the same as my observations from last Thursday. So you can introduce a seasonality instead of 24 hours of 168 hours. You can even go for 365 days in some cases, if that makes sense. But these are all possible options. And these are things that you should build before you start building very sophisticated neural networks for your forecasting problems. Once you do build these, then it will already give you a good estimate of how forecastable a time series is and how much can you get by just this very simple basic model. The second thing that you may want to also baseline with, and these are increasingly popular, are things that are already pre-implemented out of the box. So there are all the forecast models that are implemented on GCP or AWS or these kind of cloud platforms, but you also have these low-code libraries. One of them we are going to take a look at ourselves today. And what you want to do is you want to see, how does this work if I simply try to forecast my time series using a pre-built forecaster? If it works better than the baseline, that's already a big win. If it doesn't work better than the baseline, then that simply means that this model is perhaps not the best, or perhaps the library that you're using is maybe not the best at defining AutoML baselines. But either way, this is something that's going to become more and more prevalent going into the future, that we will have more and more smart AutoML pipelines to make forecasts for a generic time series. So you will always want to baseline your own algorithms against both of these two benchmarks. All right, now we get to the crux of it. This is going to be a very quick introduction to how to build a forecast model, because we will spend most of the time on actually building it using Python. So I don't want to belabor the point just talking about it. But all in all, what I want to say is that you can think about this in terms of 3 discrete choices that you can make on a very high level when you're building a forecast model. On the one hand, you have your input features. On the other hand, you have the choice of outputs. So what exactly are you forecasting? And in between these, you have quite a lot of freedom on deciding what function approximation technique you're going to use to map the inputs to the outputs. Again, there are many choices in these 3 elements, and we are going to quickly run through them. And then in the tutorial, you will be able to also see how changing, for instance, the input features can drastically improve or degrade the performance of your forecast models. So that's the first thing that we want to talk about. That's the feature selection. The feature selection problem is basically what exactly are you going to use to forecast the thing that you're interested in. In the case of electricity demand forecasting, this can be the historical data of electricity demand, but it can also be climatology features. So how hot or cold it is, how much wind is blowing, that kind of stuff. It can also be things like how expensive electricity is, what day of the year is it, and also like, is there a big local event going on or not? So all of these are features that have been used by people to build electricity demand forecasts in the past. There are also other choices with your input features as well. Like the first one of these is the typical problem of how do you build your data set or the corpus? Is it going to follow a sliding window approach, or is it going to follow an expanding window approach? Now, this is a very simple concept, but people sometimes make it more complicated than it is. What it really means is that when you have initially this amount of data available, what you're going to do is you're going to fit your model either using all of it, or you're just going to keep the actual window length fixed. So as you get more and more time, as you get more and more data, does your training data set size increase, or do you keep it constant? And there are pros and cons for both of these. So if you follow the expanding window approach, now what this is going to do is that it is going to build a forecaster that has access to all the historical data that you have seen so far. One possible problem with this would be that you would now remember perhaps too much. And this was something that we saw after the COVID lockdowns, that forecasters which remembered too much of the past were not really very adaptive anymore. So that's, of course, one problem. The other benefit of this is, of course, the opposite, that now you have a lot of data and you can fit a much more detailed model to it. So it's like one or the other, and you really have to test both to see which one works the best for you. Finally, in terms of building a forecast model and the input features choices, you can do, and you should probably do, a lot of feature transformations. Now, these can be as simple as normalizing all of your features so that they are in the same value distributions. This is typically recommended for models like neural networks or things like those. But you can also think about this as simply transforming one set of features into a separate set of features. Like, for example, if you have holidays, how do you encode them in your data so that you can use them to create these forecasts? So that is something that you also want to think about. And then you also want to think about how do you encode these into features that are usable by the models that you're building. We won't really delve too much into this, but as I'm going to talk about in a bit, this has been known to really influence the accuracy of forecast models quite a lot. Okay, then the second thing is the choice of outputs. So what exactly are you predicting? And here there are two concrete things that you want to keep in mind. So the first one of these is whether you're making a forecast which is a point forecast or an interval forecast. Today we are almost exclusively talking about point forecasts, but possibly at a later date we can have a follow-up session on interval forecasts. But in terms of point and interval forecasts, the real difference is the uncertainty estimates that you can provide versus that you don't provide. The second difference is that you can build a recursive forecaster, or you can build a direct forecaster, or something that combines these two in some way. And the difference between these two is quite simple. In a recursive forecast, what you do is you predict the next time step, and then you basically recurse on this forecast. So you assume that the forecast that you have just made is actual reality, and then you use this forecast to make the next time steps forecast. And then this allows you to make arbitrary length forecasts. So if you want to make a forecast on time horizon of 1 year, a recursive forecast, which only gives you a forecast for 1 day, would allow you to do that quite easily. So that's the benefit of this. The obvious drawback to such kind of approach is that it has a very high bias. As the time horizon grows, the error compounds basically. So your forecast gets less and less accurate over time because the error is compounding. The other approach on the other extreme is a direct forecaster. And a direct forecaster simply says that build a forecast model for every single time step that you want to predict. So if you're trying to build a forecaster that makes 20 steps ahead forecasts, then you will have 20 forecast models. If you're trying to build a prediction model which predicts 200 time steps into the future, this will require 200 models, and so on. So you can already see that this perhaps is not very scalable, even though it, of course, does not really have the compounding of errors that recursive forecast models suffer from. So it's all about trade-offs, and in practice, what many people use are things that are somewhere in between. So there is a rectify algorithm from Rob Heineman's group. There are other approaches as well, but there are also things like neural networks, which can automatically predict multiple time steps with just a single model. And those provide like a pretty good trade-off between the high bias of recursive models versus the low scalability of direct ones. This picture kind of summarizes this idea, so I will not really go into this. And in the interest of time, let's move on to the final section, which is on model comparisons. So we already talked about how do you decide if your forecast model is good or not. That's one thing, but the other thing is also, at this point, you can build 10,000 different forecast models for any time series. How do you decide if one is actually better than another, or if they're exactly the same, or if you just cannot tell? So in traditional machine learning, how you would choose between one predictor versus a different predictor is often by splitting your data set into a training set and a test set. Sometimes you can also split it into a training set, a validation set, and a test set. This, unfortunately, is fine in some instances, but especially when you don't really have access to a lot of data, then this does not remain feasible. And what people go for is something known as cross-validation. So instead of fitting your model to the entire training set, what you do is you split your training set into small chunks of data, which are known as folds, and then you fit your model on one or more of these folds, and then you test it out on the others. This allows you to create statistically significant conclusions about how good your forecast model is. And then you can compare across multiple different forecast models. Unfortunately, this is not really true, because this scheme only works for non-sequential data. As soon as you have some time series element to the models that you're building, this scheme breaks down. Primarily because if you think about it, there is a lot of data leakage that's going on if you have sequential training data. So if you assume that the model has seen this data and this data, then it can already basically kind of infer something about this thing that's missing in the middle. And now it's suddenly an interpolation problem rather than a forecasting problem. So this is not really how you do cross-validation for time series because of this obvious data leakage. How you do it is something known as forward chaining. Some people also refer to it as backtesting, but there may be like some small subtle differences between these terminologies, but the overall concept is the same. And the idea is that if you have this long time series, let's say for 1 year, you want to split it in a sequential manner. So first, let's say that you build your training model using 4 months of data, then you make the predictions for the next month of data, then you compare multiple models on this forecast, then you take a step further, you repeat the whole process again, and you continue doing this until you get to the end of the time series. This allows you to have like basically a statistically significant estimate of how good your forecast model does in many different situations. Because consider the alternative. The alternative would be that you would use 90% of your data to fit the model and then simply test it on the last 10%. This doesn't really give you any real insights about how good your model is, because it could be that, for example, you have fit your model to the first 11 months of data, and the last month contains Christmas. And that may not really be very representative of what has happened in the first 11 months. So maybe you don't want to draw meaningful conclusions about the forecasters using just 1 month of data. Right. So this is the last section, and then we can head off to the tutorial. I'll keep it brief, but if you have any questions, again, feel free to send them over.
Can I ask you a question?
Yeah, go for it, please.
I have question last this. Can you show me last figure? This figure, last one.
Yes.
That's nice. Yes, this one. In this case, the first time you try, like build the model using like an example 5 months, right? 4 months. After that, you use 1 month for testing this model, right?
Yes, so that's just like an example, but the idea is, yes, that you successively increase the size of training data set. So first you use 4 months of data, then you use 5 months of data, then you use 6 months of data, and so on.
So that in this case, for example, anyone, it's like it's correct if you use like 6 months or 7 months to test this model, like June, July.
I'm not sure I understand the question. Sorry. Sorry.
I mean, here you say the first time training the model. After that, you can use 1 month. Like if you use until April, after that use May to test this model. If I'm wondering if possible to use like also like 4 times or 5 times like June to test this model. It's correct, and August until.
Yeah, I mean, sure. I mean, but the thing is that this you can relate this back to the expanding versus sliding window approach that we talked about earlier. So here what we're using is January to April, then January to May, then January to June, and then so on. But you can also always just like keep this fixed to 4 months. And then you would go from, instead of January to May, you would go from February to May, and then March to June, and then so on and so forth. I don't know if that's what you were asking.
Yeah.
Not sure.
Yeah, I think.
But the thing is that you want to do this to make sure that you have a statistical estimate of how good your model is. The actual makeup of that model or what features it uses, that's something for you to optimize over. So you really have to try many different combinations. And in practice, what's best typically is that you want to combine those together. So for example, you want to have a very short window for a forecaster, and you want to combine it with a forecaster that has quite a long window. And then if you combine those optimally, then you get the benefits of a forecaster that adapts very quickly to changes in the signal, to one that memorizes a very long history of the signal. And then you really want to understand like which regime are you operating in at the moment, which is also the question I feel from Hamza. Is it not always best to use a complete year for load forecasting? Any data set that's less than a year will always have some missing part for the complete seasonal set. Yeah, that's true. I mean, in research, I remember many years ago, we were discussing that we would ideally want to have 3 years of data for buildings before we start making forecasts, because then you can even have like slightly robust estimates of what the seasonality looks like. Unfortunately, in practice, that's not always the case. So I remember at a company, we were even having discussions about making forecasts with as little as 2 weeks of data, at which point there is not really much that you can do to split it between test and validation and training sets. So it's really what your boss tells you in the end. But in terms of good forecasting practices, then yeah, you're correct that you would want to have seen at least the entire seasonality of the data before you start to make forecasts for it. Okay, then a couple of quick conclusions from some recent energy prediction challenges. I saw that there was someone from Singapore here in the call. So this is a competition that was run by the Buds Lab in Singapore. And a couple of conclusions that came up recently in a paper. Yeah, so Matthias is here. So yeah, this was a competition run by Clayton Miller's lab. The idea was that they provided access to electricity demand data for 1,500 buildings, and then the idea was to build forecasters for all of these buildings, so we could try to reduce the energy demand on the buildings. And quite a few different conclusions came out of it, and quite a few papers also. So I highly recommend those papers as well. But the two most striking conclusions for me are that in the winning entries, the most important step was the pre-processing and the data transformation. So it wasn't whether you use a fancy neural network or if you did some other expanding versus sliding window approach or something like that. What really mattered the most at the end was how you pre-processed your data, how you cleaned the data, and then how did you transform features into a way that was easily captured by the forecast models. Then the second thing that also came out of this was that deep learning models typically underperformed gradient boosted models. So I know that there is a big trend to use deep learning for everything. I'm also guilty of it myself in the past. Yeah, that was one of the key conclusions from this, that especially since it was a small or medium-sized data set, even though there were 1,500 buildings, it was still the case that in the end, gradient boosted models were just much more effective than alternatives like deep learning, but also simpler models like ARIMA models and things like that. So when you start building your own electricity demand forecast models, well, these are just findings from research. They're not necessarily going to hold tomorrow, but that's the state of the art at the moment. The second competition is actually from last year, which was run by Blue Wave AI. This was an IEEE competition where the idea was to predict electricity demand in the post-COVID era. So COVID really disrupted electricity supply in many countries and regions. For instance, in the south of Europe, in Spain, in Italy, in France, there were deviations of 10 to 15% quite clearly on a national scale. In the north, this was slightly less, so it was around 1 to 2, 3, 4% in the Scandinavian countries. So it really depended on where you were in terms of the disruption, but that also meant that there were significant challenges for the transmission system operators to make sure that there was enough generation, or that the electricity prices were not just completely going into the negative territory. So it was a significant challenge at that point. And then the question is, how do you build models which are very accurate, but also which very quickly respond to these deviations in real life? And some of the key conclusions from this competition was that modeling this kind of stuff explicitly is extremely important. So if you don't have features like holidays or special days or things like that, then this is really going to affect the accuracy of your forecast models. And this is also something that we will see just now in the tutorial. The other thing that came out of this was that ensembles really improved the forecasting accuracy. This is also something that we have seen in forecast competitions for the last 2-3 decades, that if you build one model, then the accuracy of that model can easily be improved by simply building an ensemble of different forecast models. And these don't even have to be that different, even though the more diverse these models are, the better the gains typically. And then finally, in your forecasters, it's always important to have an understanding of how your data is changing. So if your input data is changing continuously and you're not retraining or updating your forecast model, then that's a recipe for disaster. So at some point, something like COVID is going to happen. It doesn't even have to be something as disruptive as COVID, but something is going to happen, and then suddenly your forecast model is just not going to make correct predictions. And by the time you have figured that out, it may be too late, because electricity prices may have gone very high or very low. And yeah, so you can have quite a lot of problems unless if you're explicitly following how the input distribution of your time series is changing over time. I will not say much about this, but I believe that the slides will be shared anyway after the talk. So you can take a look at this later. But now let's move ahead to the demo. But if you have any questions, then feel free to interrupt and ask. Otherwise, I will switch over from this PowerPoint to the Jupyter Notebook. All right, so please let me know if you can see the Jupyter Notebook.
Yes, it is visible.
Okay, great. Thanks, Harsha. So yeah, so I hope that this is not completely new for everyone, this whole idea of Jupyter Notebooks. Well, if it is new for anyone, then this is just like a browser-based way to run your Python scripts. It's very interactive. So it is basically interactive Python. That's what the extension means literally, that this is an interactive Python notebook. And the best thing about it is that you can really include a lot of documentation into the notebooks. You can export this as PDF files or LaTeX files or whatever, and you can run your code directly in the browser without having to install something like PyCharm or something like that. So it's very good for rapid prototyping and experimentation, but perhaps it's not really very suitable for building complex products. So to build quick forecasters, it is really quite fine. This script is also going to be shared with the participants later, but I can already share my GitHub repo in the chat. And then if anyone wants to take a look, then feel free to. But you can just follow along with my run through as well. Okay. So any questions, feel free to interrupt as usual. But the idea with this notebook is that we want to show you how to understand electricity demand, but also forecast it. So really build your own first forecasters, and not just like very bad ones, but forecasters that perform better than the baseline, and forecasters that perform better than, let's say, hopefully at some point, the transmission system operators forecasts themselves as well. Of course, we are not going to take you that far in just half an hour, but yeah, I'll be happy if someone can do that in the future. All right, so the way this works is that you simply run the notebooks by basically Shift Enter. There are two types of cells here. This one is what's known as a markdown cell, and this one is what's known as a code cell. The code cells get executed by the Python compiler or interpreter or whatever it is, while the markdown cells only get formatted and printed. So in the beginning, we installed some libraries. I don't need to do that because that is already done. And then we import all the libraries that we are going to use in this notebook. So there's nothing special here. But the more interesting thing is, of course, the data set that we are going to be working with. And this is also available at the GitHub repo. So you can play with it later. It's in the Parquet format, but it doesn't matter. So you can simply read it into pandas very easily. There are 3 fields in the data set that we are providing. The first one is the time. So that's the calendar features, that it goes from the 1st of January 2018 till the 1st of January 2020. This is intentional because I did not want to complicate it too much with the COVID business. Then there are 2 fields that we have here. The first one is the load. So that's in megawatts, how much electricity demand is there in Belgium. And the second one is the temperature readings from a sensor, which is perhaps not very accurate. So it's a slightly noisy sensor of temperature in some place in Belgium. So you can start off by doing a bit of a feature transformation, because we already see that our load is in the thousands. Our temperature is of course, not going to be in the thousands. So we simply convert our load data set to gigawatts by dividing it by 1,000, nothing special here. As the next step, what we do is we want to create some additional calendar features. At the moment, what we have is simply the date or the date time for each individual demand. By the way, notice that this is hourly data. So we have data for midnight, then 1 a.m., then 2 a.m., then 3 a.m. So we have like hourly sampled demand data. What we want to do is we want to extract interesting features from this date time field. And one interesting feature is simply the day of the week, because you can think that on the weekdays, the electricity demand is going to be different than on the weekends. A different feature that could be also of interest would be the hour of the day. And here again, you can think that during the middle of the night, the electricity demand is probably going to be lower than during the afternoon hours, for instance. So it's very simple and easy to do this in Pandas, that you simply use the datetime library and you extract the day of the week and the hour of the day, and you assign those as new columns in your data frame. And that simply gives you the load, the temperature, the day of the week, and the hour of the day. Note that the day of the week actually goes from 0 to 6, where 0 corresponds to a Monday, I believe, and 6 corresponds to a Sunday. And the hour of the day likewise goes from 0 for midnight to 23 for 11 o'clock at night. Now, at this point, remember what I said earlier about encoding features, because at this point, what we're doing is fundamentally encoding the day of the week as an integer that takes on 7 different values between 0 and 6. And likewise for the hour of the day, where we are encoding the values between 0 and 23. But what this is not really telling the model is that midnight is actually closer to 11 o'clock than it is to 4 o'clock in the morning. But if we encode our data set in this way, this is kind of misleading for the model. So even though we are doing this in this tutorial, what you would want to do as a possible improvement for your model is to encode this slightly differently. One way that people usually do that is using cyclical encodings, where you would transform these into a way that 0 is actually closer to 23 than it is to, for instance, 4 or 6 or 12 or something like that. So just be aware that even though we are not doing that in this tutorial, you would theoretically want to do that to further improve the model's performance. Okay. Then we also have, how do we build this model with the holidays in mind as well, because we can also think that on holidays, the actual electricity demand is going to be different than on non-holidays. This is again quite simple, using the holidays library, that we can extract the holidays from Belgium and assign that to a new column in the data frame that we have. And then in the second line of code, what we do is we simply go from the name of the holiday to simply encoding all of them as binary variables. So we simply say whether it's a holiday or it's not a holiday. If it's 1, then that means that it's a holiday. So we do that. This might take a while because it's encoding all of them individually, but it's done. if you want to see what kind of holidays people enjoy in Belgium, then you can do that. But by the way, just as an indication, you can replace this BE by US or UK or whatever, and that will also give you the country holidays for the country that you are making your electricity load forecasts for. So in the holidays, you see two types of holidays, basically. Ones that are fixed from year to year. That's the New Year's Day or the Christmas. So those are fixed, just like the National Day is also fixed. But then there are some which are variable. So for example, Easter is on the 1st of April in 2018, and it's on the 21st of April in 2019. So it's quite easy using this library to encode this information, because otherwise, if you had to do it manually, then this would be a nightmare, because then you would have to figure out all of these details by yourself. So this is great for technology. Yeah, so Eric mentions that in some countries, you can even select holidays by region inside the country. That is true. In Belgium, I think that it's not possible, but yeah, I think that since we are taking a look at the entire country's demand anyway, it doesn't really matter that much. But you can always have like a disaggregated holiday feature as well for big countries like the US or Germany or something like that. Okay, then you have, so here what we do is we simply smooth out the temperature. So instead of simply calculating the temperature itself, we make this a bit smoother by averaging it in the form of a rolling average over a 2-week time window. This is simply done to smooth out some of the random variations in the temperature signal, and it basically just leads to a more smooth profile for the temperature. But okay, that's all the temperature and load transformations. What's next is we get to visualize the data now. And if you look at the data, this is the electricity demand data for the entire year, where you go from well, basically in the winters, you have the highest electricity demand in Belgium, which goes between typically 9 and 13 gigawatts. And then during the summer, it falls down to 7 to 11 gigawatts, more or less. And then it follows this cyclical pattern from year to year. Around Christmas period, you get another nasty rapid drop, which goes back up very rapidly. But then this is like a big issue for the grid operator to predict accurately and also plan for accordingly, because at this point you suddenly have to ramp down production quite rapidly and then ramp it up again quite rapidly. So there is that. And then hopefully you need to have forecast models that can somehow capture this, right? Because this is like something that you're probably going in this direction and you're hoping to go in this direction, but instead it goes something like this. So this is quite difficult for your forecasting models to capture accurately as well. Okay, then the next thing, and I don't really think that I need to run these cells, is that you want to take a look at, so this is using the library called Altair, that we are going to build some nice scatter plots to see the influence of different variables on the electricity demand. So this is the exploratory analysis part. And here what we see is that for the weekdays going from 0 to 4, the distributions seem to be quite uniform. But then on Saturday, the actual median or the mean of the data has shifted downwards quite considerably. And then on Sundays, it's even further lower by, let's say, like half a gigawatt to 1 gigawatt. So if you know this information, that what day of the week it is, you already can say something about where your expected electricity demand is going to be. The second thing is making use of these holidays as the feature that we introduced earlier. And here you can see quite clearly that if it's a holiday, then the probability of the load being much lower is quite high. So it's typically going to be between 7 and 10 gigawatts. While if it's not a holiday, then it's just like 7 to 13 gigawatts and a pretty big, well, spread around the expectation. Finally, you also can plot this for the diurnal variables to see the variations between the hours of the day. And here again, you can see that during the middle of the night, it's between 7 to 11 gigawatts, more or less, while during the day, it was between 8 and 13. So given all of these features, you can already tell that, for example, if it's going to be the nighttime of a weekend, then it's probably going to be somewhere in this region. While if it's the afternoon of a summer day, then it's probably going to be somewhere in this region. And now you just have to build a forecast model that encodes this information. Okay, final thing. We can build a scatter plot also between the smooth temperature and the actual load on the grid and fit a line to them. And if you do that, then we see that around 0 degrees, the expected load is around 11 gigawatts, while if you go all the way to 10 degrees, then it's already fallen by more than 1 gigawatt. And if you go all the way to 20 degrees, then it's fallen by roughly 2 gigawatts. So you have like this quite strong dependence between the temperature versus the actual expected load. Okay. Finally, to tie this together to the things that we were talking about earlier in terms of temporal aggregations, you can calculate the correlation coefficient between your load and the temperature, and that's around minus 0.3. So as the temperature increases, your load goes down, which is what we saw. But you also see that if we simply resample all of our data to the daily scale, so instead of working with an hourly scale, we work with a daily scale, the correlation goes even stronger. Sorry. And if you go to a weekly scale, it becomes even stronger. So this is really an indication that the data is still rather noisy on low aggregation levels. And as you smooth out those by working with higher and higher level aggregations, just more and more of it gets explained by very simple things like how cold it is it a holiday, is it a weekend, stuff like that. All right, so that's all for the exploratory part. Now to build the actual forecasters using the darts library. This is using the from data frame functionality from darts that you simply build a time series from the data that you have. So in this case, we are taking the data frame that we created up like in the beginning of the notebook, and we're saying that load is the actual value that we are interested in forecasting, which is true because we don't really want to forecast the temperature or whether it's going to be a holiday tomorrow or not, right? So we are only interested in forecasting the load, making use of those exogenous variables if we can. So that's the first part, that we have defined our data set. Then the second part is to define the actual backtesting model that we discussed earlier in terms of how do you evaluate forecast models in practice. And this is done using the historical forecasts utility inside darts. So just take a look at this. But what this is doing is basically what we discussed earlier, that this is taking all the data set before the 15th of October 2019 as the training set. And then after that, it is basically repeatedly fitting the model and testing its predictions to calculate the mean absolute percentage error. Right. Okay, any questions so far?
Actually, I have a question. I'm wondering about when you just calculate analyze the relationship between load and the temperature, the relationship was like negative.
Mm-hmm.
You mentioned when the temperature temperature is increasing, the load might be decreased, right?
Yes.
I'm wondering if like I know if there is like heating heating season and the cooling season, when the temperature like I
Yeah, so that's correct. I mean, like this is only for Belgium. If you have a cooling dominated region like India or Pakistan or Australia, for example, I suppose, then it would be very different. So we already see this for Pakistan and India quite clearly that this is quite different. So the actual energy demand peaks during the summer, and then it's very much positively correlated with the with the actual cooling demand. In this case, what you're seeing is the prevalence of the heating demand. And then during the summer months, there is not really much cooling going on in Belgium in general. People also leave for summer holidays. So it's like all in all, not really that much happening. So you have many things coming together. And then that's one reason why you typically have a very low energy demand during the summer months.
thank you.
But if you even go down to Italy or I suppose one of the southern countries, then you already get quite a different relationship between the temperature, or maybe even a bit more complicated relationship where you would have increased energy demand in both the winter and the summer and lower energy demand during the transitional months, for example. So it's just the case for Belgium and the Nordic countries that it's like a very much heating dominated area. Okay, but thanks for that. All right, then, you have constructed your data frame from the time series that we created. Now you have created an evaluation model. The next step that's left is to actually create a forecasting model, which used to be the most difficult part, but using these low-code libraries, it typically takes like 1 to 10 lines of code to build your own forecasting model. And here what you're seeing is a very simple naive seasonal model, which is built using 1 line of code, and then you fit it using your training data. And then finally, you simply evaluate it using this script that we just created. And now if you see what's happening here is that it's simply copying the values from 24 hours in the past to make its forecast. So that's why it's always messing it up on the first day of the weekend. And then it's always messing it up on the first day of the week. So on Saturdays, it's copying the data from Fridays, which makes it a very bad forecast. And on Mondays, it is copying the data from Sundays, which again makes it a very bad forecast. So that's one big problem with this. The other big problem is, of course, also that it has no idea about when there is a holiday or no holidays. And of course, that it doesn't take into consideration the temperature influences either. So all in all, it's a very bad model, but it's the baseline. It's around 5.67% in accuracy. So now the real question is, can we improve on this? If you look at the error signal smoothed out over time, then you see that this is like a very cyclical pattern in your error, which is basically what I just mentioned in terms of the weekend and weekday problems. If you calculate the autocorrelation function on this signal, which I haven't done in the notebook, but you can very easily do that using the darts library or the stats model library, or like even I think in matplotlib you can do that. Then you will see that you have a very clear weekly periodicity in this error signal, which identifies that you can really improve this model, which shouldn't really be that surprising, but okay. So what we do instead is we build a model using the weekly seasonality. And now what you see is that we are copying values here. So when we are forecasting here, then we are copying values from here. Then when we move forward by 1 day, then we copy values from this, and then so on until we reach the end of the test data set. Now, you can see that the forecast error has improved or has gone down. But one big problem with this is what happens during the Christmas period now, because previously it was adapting quite quickly. So it figured out that it had gone well, it had done really badly. But then the next day, it really copied the value of the Christmas, and the error was quite big, but not really astonishingly high. In this case, what happens is that the error is absolutely enormous. This is like 2 gigawatts, which is like almost 20% of the overall energy demand that you can expect to see at this point. So that's an enormous error around the Christmas period. And the reason for that is because it's simply copying for the Christmas week the values from the week before that. So that's not really surprising. That is also a very bad model. So these are the two baselines that we have established. Next, what we can take a look at is a theta model. And the theta model is actually a very simple model, but it has surprisingly won many different forecasting competitions. It tries to fit the data, but it still doesn't really take into consideration any exogenous variables like holidays or, for example, temperature data or anything like that. But you can already see that it has considerably improved the forecast errors, and you can simply build it calling this command. So you just specify what the seasonality of your data is, and you're done. So it doesn't really take a lot more than this to create this model. And you can see that some weeks it's very accurate, like this week, and some others it's not so accurate, like on this week around the Christmas time. And you can also see that here, that there are a few random spikes in your forecast accuracy around the Christmas period. That's to be expected. But then you also see 2 spikes here and then here. And then one of them is the 1st of November, and the second one of them is the 11th of November. And guess what? Both of those are public holidays in Belgium. So this model completely missed the forecast on those days as well. Not surprising either, but let's see if we can start to build our own regression models that can somehow rectify these problems. The very first approach we build is using a linear model, which simply takes into account the previous week of data to simply see how this model performs. It doesn't really perform very good, but that's fine because we only did this to test the model out. As the next step, what we can do is we can experiment with the historical lags, but that doesn't matter too much. What really matters is that we can start to provide exogenous variables like the day of the week, the hour of the day, and the holidays, and also the actual temperatures that are expected at those times. And that really is what we have been building towards for this entire talk. So if you start off by using just the day of the week and hour of the day as future regressors into our model, this is how you do that. It's very simple. You simply have to pass the future covariates. Then what you get is around 3.85%. And this is around the same accuracy as what we got with the theta model. It's basically pretty much the same. And then for the theta model, what we saw was that the error was typically concentrated between 0.25 and minus 0.25, except for these holidays. So now we can compare that. That this is pretty much still kind of the same as what we had previously. Christmas is still very bad. And then we also have the complementary peaks in error around 1st and 11th of November. As the next step to fix this problem, of course, you include your holidays in the forecast model, and that already substantially improves the forecast accuracy further. So you can see now that the error on the 1st of November, for instance, is pretty much close to 0. So this has well, more or less solved that problem. But now we see that the Christmas period is still an issue. Okay, but we have a couple of questions. What is the seasonality period of 168 exactly? Yep, so Hamza is correct. That's just the weekly seasonality. All right, Carlos, does the hour shifts in spring and autumn make a difference? So since we're working with, well, that's basically a great question because that's always a big problem with forecasting and building forecasts and stuff like that, that the data is switching 1 hour into the future and then 1 hour backwards. And then you're like, okay, what's happening? But in this case, what we're doing is we are simply working with timestamps. So what we did was we built the data set using the timestamps, and we completely ignored that problem. So I suppose that there is going to be an effect of people shifting their behavior somewhat because of the shift in the calendar, but that's not really something that we are taking into consideration in the data set or the tutorial. But yeah, that's a great question. All right. So Khalil asks, can Bayesian dropout be used to estimate uncertainty in the forecast? If you're using a deep neural network, then yes, I suppose so. So yeah, I mean, we have used that in the past, but it's a bit difficult to calibrate those Bayesian dropouts, to be honest. But yeah, I don't see any reason why you cannot do that. Okay. Then, so now we are at 3.52%, which is, as you will remember, a huge improvement already over the initial model that we built, which was 5.7 or 5.3. So that's pretty good. But we can still do a bit better by incorporating the temperature into the model as well. And if you simply do that, then you already get down to 3.2%, which is, well, much better than what we started with. And now if you take a look at the forecast errors, they're basically like very close to 200, 300 megawatts. So very small errors. And the only really big error that we're still getting is around the Christmas period. And now at this point, you may be wondering like, okay, I've already added a feature for the Christmas holiday. Why is this not fixed already? And the reason for that is because if you remember the initial time series, it's not as simple for the Christmas period, because while on every other holiday, it would be a localized effect, for Christmas, what you see is a whole week or even 2 weeks of deviated electricity demand. So it's insufficient if you simply use one feature to specify the Christmas period. You may probably want to have like an additional feature to specify that this is the Christmas period. And then, for example, if you have data for more than 1 year, then you would be able to fit that. Of course, before you have data for 1 year, you really don't have any way of doing that. So one way could be to simply specify the entire period between New Year and Christmas as a holiday period. So there are all these hacks and tricks that you can do to somehow further improve the performance during the Christmas period. One last thing, and that's the very last thing in the tutorial, that so far we have simply used a regression model. There is really no reason to simply use a linear model. Like Khalil mentioned in the chat, you can build a Bayesian deep neural network or literally anything else that you want. Darts supports all the models in scikit-learn, so you can simply replace the model by anything else that you feel like. For example, the ridge model or lasso or SVMs or whatever. And the way you do that is by simply specifying here the model type. And that will simply be model equals linear model dot ridge and then the hyperparameter, so something like that. And then you have a new model type. And the final thing that we see is by replacing that regression model by the light GBM model. And so basically we do two changes. The first one is we replace the model from the regression model, which is a linear model by default, to a gradient boosted model, which recall from the talk is, well, de facto performs the best in many competitions. So we replace the regression model with a light GBM model. And the second thing that we do is we specify the output chunk length. And this is simply like, in a way, going from a recursive forecast model to a direct forecast model, or something that predicts multiple time steps with the same model. So even though we are building the same model, it's basically saying that it's going to be able to predict the next 24 steps in one go. which is fine. I mean, it's just a hyperparameter to test out. Like you can see like, okay, I set it to 1, how does it perform? I set it to 24, how does it perform? And so on and so forth. And then what that gives you is a forecast accuracy of around 3.0%, which is excellent. Especially if you consider that most of this is basically like around 2%, and it's only around the Christmas time that the model is really struggling still. So that's, I would say, as the next step in the forecasting journey, that's something that you can try to fix. But all in all, if you have a forecast model that performs like around 3% in terms of the Belgian load, that's pretty much in line with what Elia comes up with at the end of the year, because their forecast accuracy averaged over the whole year is typically around 2.5%. And if you can already, after 15 minutes of coding, build a forecast model that has a 3% accuracy, I would, well, consider that a big success. So there are some next steps that I mentioned at the end of the tutorial, but that's really up to you to try or not to try, depending on how interested you are. And if you have any questions, then feel free to send me an email later or just get in touch. But yeah, that brings us to the end of the tutorial.
Can you please go back to the next steps, if you don't mind? Thank you.
Yeah, sure. Wait, I just have to find the notebook again. But yeah, okay, here you go.
Thank you.
Yeah, so like the ensembles are very easy to integrate at this point because you have already built many different models. Like even though you didn't realize it, but all of these are separate models. So what you can even do is you can start to combine the model predictions from the light GBM model with, for instance, the linear model, with, for instance, the theta model. Already gives you 3 different models in your ensemble. But then you can also start to vary how much input data do you give. For instance, what type of model do you use to build the model? So all of these things you can vary, and very quickly you have like a pretty sizable ensemble of models that you can then simply average or use the darts library to learn the weights that you should assign to all of those models in the ensemble. I have to emphasize that typically it's very difficult to simply beat the average of multiple models in an ensemble. But if you really can figure out whether one model works better on the weekdays and then a different model works better on the weekends, then you can do some kind of weighted averaging, and that sometimes leads to better performance as well. Okay, so then I can stop sharing, and yeah, we still have some minutes, so if anyone has any questions, now's a good time. All right, thank you for joining, everyone. Thank you for everyone who said thank you.
Thank you very much, Hussein, for your interesting session. And thank you very much again for accepting our invitation to be our resource person today. And thank you very much, everyone. If you have any question, please feel free to reach out to us, and we'll try to do our best to answer your questions. Thank you, everyone.
Maybe I have
Thank
a
you very
quick
much,
question.
Harsha. Yeah, go
Will
for
there
it.
be a second session? Because you mentioned it really quickly, but I'm not sure if it's really the case.
Well, that depends on whether Harsha and Bahman invite me back or not.
We will surely invite you.
All right. Yeah, you should. You should. All right.
Okay, so
Thank
I
you.
sent my email also in the chat. So if anyone has any questions, then please feel free to send an email. Might take me a while to get to it, but yeah, I will do my best. Okay, thank you very much, and have a good day, everyone.
Thank you very much. Have a good day.
Thank you very
Stay safe.
much.
Bye.
Thank you.